Hello, everyone. I want to use this video to walk you through our lecture number 4 about air humidity and precipitation. Okay, so let's get started. Okay, so lecture presentation number 4 is for our next module. Let's see. Module number 4. Okay, so here is my presentation. You are going to read, please read your textbook, Essentials of Meteorology. This textbook, you can download it from our Canvas, the shell. You're going to read chapter 4 and chapter 5 in next 2 weeks, week 7 and week 8. So this is the lecture outline. In this week, the discussion, you're going to reflect on what you have learned in the top 2, I think. Let's see, our discussion is air humidity. Okay, so we are going to summarize the hydrologic cycle and atmospheric circulation and evaporation and condensation. Okay, don't forget to post one of your questions to challenge your classmates. Okay. Okay. So, well, water is important. Water, you can see 3 phases in Earth's environment, right? Solid, gas, and liquid. Let me present solid, gas, and liquid. Why they have those 3 phases? Well, that is related to the molecular structure of water. You can see water is H2O. So hydrogen atom and oxygen atom, they form this like angle shape, this structure like a check mark, right? So, well, you will have 2 ends. We call that 2 extremes in terms of electric charge. Okay, so oxygen carry negative, hydrogen carry positive. So you can see negative and positive, they attract to each other, right? So you will form this bond. We call that hydrogen bond. Hydrogen bond. So how tight this hydrogen bond is actually determines what phase, okay, our water is in. So you can see if the water molecules, they connected by the hydrogen bond so tightly, they form this hexagon texture over here. Okay, structure, I should say, structure. You will see our water is in solid phase, it's in ice, it's ice. But when you add the energy absorbed, right? When you add the energy, apply energy to solid ice, basically you melt it, you will turn that into liquid water. But that energy is not going to be used to increase the temperature of ice, okay? Or the liquid water. They still stay 0 degrees Celsius or 33 Fahrenheit, okay? But the energy is used to break apart this hydrogen bond. Okay, so this energy, we call that latent heat. So you can see latent heat is very, very interesting and also play a huge role in our atmosphere and Earth's ground energy exchange, as you have learned in the previous module, right? So you can see here, if you continue applying energy, latent heat to liquid water, you're going to vaporize your liquid water to gas water, right? So you can see the hydrogen bond is even further compared to the liquid. So you need energy for evaporation, right? But when you go opposite direction, condensation and freezing, they both release energy because you don't need that much energy to keep the different water molecules away, right? So you will release the energy to the atmosphere, to the surrounding environment. So let's review our energy exchange through latent heat, right? You evaporate your water from water body at the ground in our lake and ocean, well, they absorb the heat, right? From the ground, from our ocean, from our lake. But when they're rising up to atmosphere, they condense into cloud, become liquid water, then release the latent heat to the atmosphere. So that is very important way to transfer the ground energy, the earth surface energy to upper atmosphere, right? Okay, so that is very interesting and important. Okay, so just fun facts. Water in atmosphere, how much, right? In what phases? So you can see if you treat the entire Earth as a whole, right? Ocean actually saline water, solid water, take 96.5%. Okay, fresh water is very little. Okay, and if you treat this fresh water as one, you can see glacier and ice caps, they take a lot of percentage, right? Surface fresh water is only 1.2% of this fresh water. Okay, and then surface other fresh water, if you break that down again for the more, well, you can see atmosphere is 3% of this 1.2. So you can see it's very, very little, but it's very dynamic. We constantly have evaporation and condensation to recycle our water and also to recycle our energy, right? Okay, so read your textbook, and here's a link. Go to NASA website, okay, USGS website to show you how much Earth on the Earth. So it's a very interesting picture. If you extract all the water out of from our Earth surface, and you can see here, well, the entire globe, the water just like this huge ball, but the fresh water is just this little, but the atmosphere is here if you can see it. So it's very interesting. All right, okay, so then water in the atmosphere, another very important concept is water cycle. So basically we want to understand where they from, hydrologic cycle, okay, on page 92, and you know how they recycle in between different earth system like hydrosphere, like atmosphere, biosphere, even lithosphere, groundwater, right? The water in our rock, in our rocks. Okay. So again, latent heat associated with each step. Okay. So atmosphere is a reservoir for water to temporarily stay. They cannot stay there forever. Okay. So that time we call that residence time. Residence time. So you know, residence time, how long they can stay there. Actually, it's very, very short. It's like even a few minutes or like up to days. Okay, that's it. But compared to groundwater, water can stay there for thousands of years. Okay, and the flow would process carry those water from one sphere to another sphere. That's called exchange or flow. Okay, during this process, you have your latent heat, either absorbed or released. Okay, so you need to know those processes, and it's released or latent heat is absorbed. Okay. All right, so then let's answer our question. Where are they from and where do they go? Okay, so main inputs for the moisture in the air, that is from evaporation and evapotranspiration. This is more specific for the evaporation and transpiration from our plants, from our land. Okay? And here, main outputs condensation. That is various phenomena you see in our atmosphere and close to the ground, including clouds, fog, dew point, dew, right, dew droplet, and also different types of precipitation. Okay, and in between, we want to measure how much water in our atmosphere. We have two ways. We can measure how much, the absolute number. That is where you want to use specific humidity, okay, mixing ratio, or vapor pressure. Okay, those can measure the absolute amount. For example, specific humidity give you absolute grams, how heavy the water moisture in the air. Okay? Mixing ratio is a percentage of the the uh, water, water vapor, and vapor pressure is the pressure specifically exerted by our gas water vapor, the gas phase of the water. Okay, so read the textbook to learn the definition. Okay, you want to summarize that in your text in your discussion. And another way, actually a more commonly used way, is how saturated the air is with water vapor. Okay, so basically our air have a capacity to hold the water. So in other words, they can only hold a certain amount of water. And this capacity is determined by temperature. Okay, the warmer the air is, the more water they can hold. Okay, so you can see here, like I use those two jars. You can see the first jar, they have bigger capacity, right? 30 milliliter of water cannot make it full at all, right? You have like 2/3 empty left. But if the capacity of the jar, like the second one, is a little bit smaller, right? So you can see same amount, same absolute amount, right? Water, 30 milliliter of water will make it half full, right? So this capacity actually determines how saturated we say your air is with water. Okay, so that is a very important concept, how saturated it is. And keep in mind, this capacity is related to temperature. Okay, so let me show you, actually you can look it up. Let me show you that chart. Here we go. You can look it up by using this chart. So you can see it's solely determined by temperature. So for example, you have temperature at 10 degrees Celsius or like 50-ish Fahrenheit, right? The capacity is about like 8 gram, okay, like this, okay, like this, 8 gram per 1 kilogram of air. Okay, so that is your capacity. But you can see as the temperature goes high, you have more and you can hold your capacity become bigger and bigger. Okay, and the actual number of water moisture, that is the same amount, cannot make this air warmer air at all, right? Okay, so evaporation and condensation. Watch this video or read this textbook to learn more. But long story short is conditions for evaporation, you need energy. Okay, you need to absorb the energy to turn the liquid to gas. Okay, and the air above your water surface cannot be full. Okay, cannot reach their capacity. If you reach the capacity, the air cannot hold any more water, so you won't see evaporation happen. Okay, another one is condensation for the conditions for condensation. That is, the air must be saturated. Okay, if the air is not full, you won't see condensation. You won't see cloud. So, in other words, if you see cloud in the sky, that means the air is full up there. Okay, because they're cold. And you also need this condensation nuclei, which is tiny particles or liquid droplets our gas water can grab up. So when they condense, you can condense on those surface, and then your droplet will become bigger and bigger and bigger. Okay, so that is your condensation. Okay, remember those conditions for each. All right, so like I mentioned earlier, to measure how much, you will have three measures you can use, okay? Specific humidity, mixing ratio, and vapor pressure. Okay, so look into your textbook page and then you can find the definition, okay? So those two become related to mass, how heavy, and the last one related to pressure. Okay, and saturation, as I mentioned earlier, how saturated the air is, you need to first determine the capacity. In other words, that is the maximum water vapor air can contain, aka saturation status. Okay, so well, that's solely determined by temperature, and you can look it up here. Okay, and then when you know the saturation, okay, you know the saturation, the full capacity, then how much actually held in your air, right? How much actual water vapor is held in your water, in your vapor, in your air. That is when you divide, okay, when you have the division times 100%, you will have your relative humidity. That is meteorologists, they broadcast every day. Okay, our air is 90% full, means you're going to see rain. Okay, 1% full means the air is bone dry. So that is it. But you can see this relative humidity can be a little bit misleading. For example, in other words, if you have a high percentage, that doesn't mean your air contains a lot of water. Okay, so you can see if the capacity is very small, you could be 100%, right? But the air, water vapor, the actual water vapor in there could be very small. Like when I was in Madison, I remember in the winter, it's super cold. When the capacity of air to hold the water is very small, okay? I see the number, the percentage every day is like uh, 90, 80 percentage, but my lips still crack. Next week, our discussion, I'm going to ask you to explore two places, okay, Alaska, Barrow versus California, for example. You will see actually Barrow have very high relative humidity, but air is dry. Okay, another very important thing is to make the air saturated. You can do two things. Of course, you can have more evaporation and more water vapor, but another very commonly seen way is to cool them when they go up in the sky. Okay, so check out this experiment to make a cloud in a jar. All right, so as I said before, if you cool your air, right? If you cool your air, you can shrink the capacity, you can make the air saturated, right? So say now your air temperature is like 70 Fahrenheit, right? How much you should cool, or to which temperature you should cool to, right? Decrease your temperature to, you can make your air saturated. So that critical temperature is called dew point temperature. That is the temperature you're going to see liquid water. So that is your Coke can. You grab it from the fridge, right? You see the water condense around the can. That is the moisture in the air. When it touch the Coke can, the air become cooled, right? And saturated. That temperature is your temperature. Okay. So when the air is at dew point temperature, RH 100%. And here is a fun instrument you want to use to measure the relative humidity. The sling accelerometer. Okay, so basically you have two bulbs. Okay, one is bad bulb. Okay, we call that because you're going to dip it into water, make it saturated. Okay, before using, and then the other one is dry bulb. Then you spin it, you see the temperature difference in those two thermometers. And you use that difference, we call that bad bulb depression to look it up. Okay, so there's a video on our study guide. Make sure you watch it. You will see these questions on it. Okay. All right. So then the next topic is atmosphere stability. So you can see our cloud is up there in the sky, right? But why they're up there? Because the air is not stable in the first place. Okay, so then what is stability? Stability is, well, it's stable, right? They want to stay there. Okay, so it's just like this little person. He want to push the rock against the mountain, against the slope, but as soon as he release the pushing, the force, right? The push, the force, the rock will go down, right? Will go down to the bottom here. So we call that stable. Same like your air. If your air is stable, even you give it a lift, it will go back, okay, to the original location. So we call that air is stable. But if it's not stable like this, okay, this little person hold the rock at the top of the mountain, okay, once he released the hold, this rock will roll down the hill, right? It's not stable. So in our atmosphere, unstable air is you give it a push, a lift, it will keep rising. That air parcel is not stable. Okay. So here I use this chart to explain the stability already. Okay, so you can read those texts to learn more. Okay. So then how to determine your air stability? Very simple actually. You just need to compare the temperature. So you can see if the air parcel is warmer than the surrounding air. So for example, here the inside air parcel, the inside temperature is 25 degrees Celsius. Okay, outside, let's say it's 15, same level, okay, same level, then this air is not stable, okay, because it's hot inside. It's like hot air balloon, it's going to rise, okay. But if inside the temperature is cooler than the environment, same level, okay, say this one is 10 degrees Celsius, outside is, I don't know, 25, 20, okay. So you can see this air is very cold inside, it's like denser, right? So it's going down, so that is stable. If they have the same temperature, your air will stay there for that neutral status. Okay, so very, very simple. Okay, but the key is how to determine the temperature. Okay? So you're going to use the rate called adiabatic rate, cooling rate. When the air going up, you decrease subtracting temperature. When the air goes down, you increase your temperature because it's getting warmer and warmer, right? So which rate you should, but this process is that adiabatic process. You can increase or decrease your air temperature without adding heat or extracting heat from your air bubble. Okay, how it comes? Well, when the air go up, the air will expand, right? And your air molecules in it will have more room to moving around, so they will slow down. So once they slow down, the temperature you can control decrease. Okay, so this is called adiabatic cooling. Inside temperature decreases without losing heat by expansion. Okay, and warming, that is when the air bubble going down, you compress the air, you make them move fast. Pressure is a kinetic energy. Okay, so you compress them, the temperature will go high. Okay, then how fast? Well, you're going to use either DALR or MALR. Okay, DALR is used when the air is not 100% saturated. Well, MALR is used when the air is 100% saturated. Okay, but that is applied for calculating the air inside. Okay, air inside. So you can see this air parcel is not saturated. So at the ground is 30 degrees Celsius. When you go 1,000 meter above, because this rate is 10 Celsius every 1,000 meter, right? So the air temperature becomes 20. Another 1,000 becomes 10. Okay, but when you go down, you need to add. Okay, but for the outside environment, same level, how you determine it? You're going to use this ELR. This ELR change a lot, okay, very frequently. So this number will be always given. Global average is this number, okay? So say our ground, the temperature is 30, okay, same thing. And you give this air a little lift, it's going to rise, right? So say today our environmental lamps rate is 6, let's make it easier, okay? Then the same level, okay, 1,000, your air will cool to what? 30 from the ground minus every 1,000 decrease 6.4, so minus 6.4, right? You'll have like 23.6 each. Okay, so you can see at this level, if the surrounding air is 23, okay, 0.6, you can see your air is colder and the air will go down actually. Okay, so that is the little calculation you want to understand in this module. All right, so here, that is basically what I just described. Okay, as long as the air is warmer than the surrounding air, it will rise. Okay, so if the air is not inside, you should use MALR or DALR, depends on RH, and surrounding air, you use ELR. Okay, and then you just compare if the inside temperature is warmer than surrounding air, same level, same elevation, then the air is not stable, going to rise. Okay. All right, so little practice. Okay, so here, for example, writing humidity 50%. Okay, you're going to use DALR, right? Okay, this one is 100%. You're going to use MALR. Okay, so calculate it, help me determine whether those two air bubble, which one is stable, which one is not stable. Okay, you're welcome to email me your results. All right, so then another very important thing is your cloud. Okay, so let's first study this tower cloud. Okay, that day I think that is one of your classmates. She sent me a cloud very like this one. Okay, how that formed? That basically is, but in the first place, your air is not stable, right? It's not saturated. So it's going to rise, the air is not stable, okay, it's going to rise to a certain level, it will become saturated. So you will see the cloud form. So you can see cloud, most cloud will have a very flat base, right? Okay, so that is your lifting condensation level. So basically when the air cool to this level, okay, they will be cooled to your dew point temperature, okay, to your dew point temperature, and then you will see condensation. Okay, you will see condensation. So that is very important. And then beyond that, your air temperature will decrease using MALR, and it's likely to be warmer than the surrounding air. You will see more and more condensation. Okay, so that is your cloud formation. Okay, must rising up to above lifting condensation level. Okay. All right, so that's why you can see the cloud usually form on one side of the mountain when the air moving up, but the other side when it's descending will get warmed up, right? So your your cloud will be dissipating. Okay, so like this. Okay, so you can see when the air pushed against the mountain, reaching LCL, lifting condensation level, you start seeing cloud and air will decreasing using 6 every 1,000 meter, right? And then when they climb over the mountain, descending, never see cloud because getting warmer. Okay, always using 10 getting warmer because the air is now saturated. Okay, so then just to summarize cloud formation. Okay, rising air, lifting condensation level, condense, right? Okay, and don't forget your condensation nuclei. Okay, here is you will have one essay question asking you to describe the cloud formation. Make sure you read your textbook and to learn the concept, the process. Okay, and beautiful cloud sharing with you. Okay, and this cloud classification, so you can see from the week 1 we started playing the cloud, right? Then, more commonly we classify it using their shape. Okay, we have 3 basic shapes: stratus, layers, right? Cumulus, cotton balls, and cirrus, the hair-like. Okay, so cirrus-like cloud we see a lot in California. They're very high, and also refers to those high cloud. Okay, and stratus, you can combine different types like cirrostratus, okay, autocumulus, right? So that's different cloud. This, tower cloud usually moisture laden, and will bring you a thunderstorm and tornadoes. Okay, and tornadoes. Okay, so the last concept is our precipitation formation. Okay, looks very complicated, but actually very comparison. Your cloud formation, your precipitation formation determined by the temperature of your cloud. Okay, if your cloud is warmer, you will have this coalescence process. Basically, yes, bigger droplet will attract the smaller droplet. Okay, so basically those two water droplets that they're suspending in the sky, right? But when they're moving around, they will have a more and more, those water droplets, they will boop, merge together and then become a larger one. And then when they will become heavier, they're falling down. In their way down, they will incorporate more, right? So that is a warmer cloud. Okay, so in Singapore, those Philippines, right? You will see a lot of this type of precipitation due to warmer cloud. But if you see snow, hail, okay, the cloud is colder actually. In the colder cloud, the precipitation formation actually is follow this ice crystal process. Because, well, basically, yes, your cloud temperature is below freezing point. Okay, you have those little ice crystals. Okay, if you have the, in your fridge, you have some ice cube. Take one out, put it in your hand. You'll feel those ice cube is very sticky, right? So that is another formation, phenomenon called sublimation. So basically, the gas water in the air can become solid, okay, in one step. Okay, so then your ice will be bigger and bigger and bigger, right? And they also kind of attract a lot of moisture. So you will form, solid ice balls, okay, in the cloud. And when they're falling down, well, maybe they will be melting, okay, they will melt. You will have some liquid rain or liquid rain plus solid ice ball, right? Hail and snow, okay. So that is your cold, a little bit different. All right, so then, those ice balls can also behave like a condensation nuclei, right? So your water can grab up and condense out. So that is your ice crystal process. Okay, read your textbook to learn the details. Okay, that is the next chapter, chapter number 6. Okay. All right. So then ice crystal process, okay, usually happen in this tower cloud because it can raising so high, okay, the updraft is so high. Sometimes they will go up many rounds. So that is why when you have this huge hailstorm, because they are turning around like what, like the air wheel, right? Well, they will incorporate more and more tumbling, okay, around. You will have more and more ice crystals form and come together. You will have this big, okay, hailstone. Okay. It's a disaster. It's a meteorological disaster, actually. People. Okay, so I think that's it. That is all the thing I want to explain on my presentation, and those are the study questions. Make sure you watch the videos on the study guide page, and make sure you can answer all these questions before you're taking the quiz. Okay, all right, so that's it. This presentation is for this week and also week number 8. Okay, so I will hold my office hours and I'm looking forward to seeing you during my office hours. Okay, bye for now.